So a little bit recap from the last class. We covered a lot of ground using our favorite turtle, and we did through examples. So apparently it might have looked like we just did some graphics display, but we did cover a lot of ground. And the spirit of the course is to help you express problems using C++, solutions to problems using C++. And the idea is if you can solve a problem by hand, and if it takes a lot of time to execute the program, at the end of the course you should be able to write a program in C++ which runs fast enough. And in the process you will also possibly learn new ways of solving problems. For example, you might learn how to design new functions, how to use recursion, things that you probably won't do by hand. So to master this course, most important is do not be afraid of using the computer, do not be afraid of producing programs that go into the computer, and if you have questions like what if I write XYZ in my program instead of PQR, just do so and find out. I'll be demoing a lot of stuff through test programs. Okay, so this is an IDE called Code Blocks, and yeah, I'll demo programs probably in the class, and you should try things out if you have some doubts. So be adventurous. However, try and first write your logic on paper before you write a program. Make sure that you have very clearly enumerated the steps of the program with rationale behind them before you start typing them out. And then we will use a lot of picture drawing because that requires calculation. We saw it in the last class, computation of the exterior angle. We mostly focused on uniform polygons, but you could also try the following. Let's say draw a triangle with sides 3, 4 and 5. So you need to do some trigonometric calculations to find the angles, right? You have to do some cosine computations. Okay, so here's a pattern with 36 repetitions. So you'll have a loop, you'll have a block that you iterate on 36 times. What will each block consist of? You would have some circle, part of a circle, part of another circle, and a tangent to one circle at a point that also becomes tangent to another circle at another point, right? So you'll have to do this, repeat this pattern 36 times, and these are things you will be able to write programs for. Okay, and this is a nice video created by Professor Abhiram Ranade to give you an idea of the kind of programs you could write making use of the turtle sim. So there's this simple CPP package. Some of you have already started installing it, and there are some interesting patterns here. The one I showed with 36 repetitions also shows up here. Now this is serially executed, which means you complete a pattern and then move on to the next. You could also write programs which parallelly drop sections of the patterns and then kind of fill them up subsequently. You could do this serially, you could do this parallelly. These are Hilbert curves. So these are, you're basically building towards Hilbert curves. So these are space filling curves. They have this fractal kind of property. The same pattern repeats itself, right? And eventually you will get them fill up the entire space. Even the gaps between these curves could be filled up using these Hilbert curves. Yeah, so you could look at a lot more examples, tree-like structures, and so on. I'll post this video for your offline viewing. So we'll build on the motivation developed in the last class and move on to formal definitions. So we start with variables, and in the process also understand how they're stored in a computer. Then look at data types and different expressions that we could build around the variables. So the outline is how to store data in the memory of a computer, how to perform arithmetic operations, reading numbers into the memory from the keyboard, print numbers on the screen, and programs based on this. So we get into more subtle details. So first and foremost a variable declaration. It's a general statement of the form, a data type name followed by a variable name. So let me start from scratch. So this int x, this is a declaration. To be syntactically correct, you need a semicolon. Double y, this is also declaration. Somebody was asking me what this using namespace std means. So you could have multiple people in a classroom with the same name, right? Do you, are there similar names here? Anyone? Abhishek. 3 Abhisheks. Okay, so 3 Abhisheks. Abhishek is good enough for the time. Right? So how do I distinguish one Abhishek from the other? So you have roll numbers. Another way is I could look at branches. Are they from different branches? Okay, they are not. But roll numbers are different. Are they from different hostels? They are not from different hostels. Different floors, wings, different rooms. So there is something that distinguishes them from each other, right? So this namespace is basically that way of distinguishing, right? So you could have functions, the same function. I gave you the example of this turtle sim, move up, pen down, forward and all, right? So now you could have forward defined in multiple so-called namespaces. So we are saying standard namespace, the default namespace that could be used to invoke functions. So I mean, beyond that we will not get into the details right now. So that's not very important. For the most of the course we will only use this using namespace std. So it's a ritual. Let's do it. Don't ask why. But yeah, if you have a question why, think of Abhishek. IOStream is just is a library that I am invoking so that I can print. Okay, so we saw examples of printing, but we'll see more today. So we already saw some examples of the print statement. So already saw examples of this declaration. So for example, this variable name could be sides here, and data type name could be int. Int is a short form for integer, and basically what you're saying here is that we have a memory in which I would like you to reserve some space for the variable called sides. So you're saying that please reserve some space in this memory, a row of the memory, for the variable called sides. I'm also additionally associating a type with this row. I'm saying that I'll interpret this row to be an integer. Okay, how this is all done is the task of the compiler, the task, and the executor. So they need to basically keep track of these pieces of information. But for the time being, it suffices to say that we are basically reserving space for storing integer values in a memory. And size is a name given to that reserved space, a variable created. Okay, so this is the example. Now, as for a row itself, the row of this memory, how is it represented? So, each row is a sequence of bits, 0, 1 bits. So, for example, if I ask you to represent 5 sides, pentagon, was it a pentagon that we drew in the last class? So 5 sides. How would I represent 5 in binary form? 5 equals, so the best way to think about it is 1 into 2 raised to 2 plus 0 into 2 raised to 1 plus 1 into 2 raised to 0. Okay, so what we have are these 3 1 0 bits, right? So the representation for 5 is basically going to correspond to 1 0 1, right? And that's what you will write here. So let's say my size value was 5 1 0 1, the rest will all be zeros. Now the size of this row in terms of number of bits is specified here to be as 32. Should it always be 32? Can it be smaller? Can it be 3 bits, 5 bits? So it turns out that typically we look at multiples of 8 as far as number of bits is concerned. So a sequence of 4 bits is called a nibble, 8 bits is a byte, and thereafter it's basically bytes only. Typically we will talk about bytes. Nibble is used only because sometimes it's easy to represent 4 bits and compute the decimal equivalent. 8 becomes a little cumbersome. Otherwise 8 is what is a standard. So we look at multiples of 8. 32 is how many bytes? 4. So it turns out that int is specified using 4 bytes. Why? Well, we want to represent a sizable number of integers. So how many integers could you specify using a byte? 2 raised to 8. And what is 2 raised to 8? 256. Okay. So a byte can specify 2 raised to 8 or 256 integers or values. I mean, I'm saying integers, but you could just think of them as values. 32 bits is therefore going to be able to represent 2 raised to 32 values. So variable declaration amounts to associating a row in the memory. But what is this memory itself? Okay, just to understand where we will fit memory in the scheme of things. Anyone here has successfully opened a PC and brought it back to life as well? Okay. So you must have noticed some of these components. So you have this CPU with a cooling fan, a lot of computation happens there. The CPU also has some small amount of memory in the form of registers which are very quick to access. These registers let you do computations, arithmetic computations, small and fast to access memory registers. You also have another component here, fast electronic memory. This fast relative to the hard disk, but it can be slower than the registers. This is called the RAM. Okay, so what you'll have is random access. So what you have in the RAM is this kind of table where you can quickly access a row. So registers from the CPU will tell you which variable to access. You will pick up the value and load it to one of the other registers. Okay, and again these are details which may not bother us in the course, but you should just know where your variable values are being stored. Now there is also a much larger storage which is available in the form of the hard disk, and the connection to the hard disk, the magnetic disk data connectors are sitting here. Okay, so this is connection to the hard disk, not the hard disk itself. So here you have the hard disk, the data cable between the disk and the motherboard. So this is exactly what we were pointing in the previous slide. Now the hard disk can store a lot of data, but they can be slower to retrieve. So what you see in the hard disk is a platter. What you see here is a platter, a disk. This is an arm which has a magnetic head. The platter itself also has magnetic coating. It's basically magnetic storage. So entire storage is magnetic. Now if you want to access some bytes or sequence of bits, what you will need to do is rotate the disk. This is a rotary motion associated with the disk or the platter, and there is another motion, a kind of arc motion that you will subject the arm to. So using a combination of the disk motion, the rotation, and the arm motion, you can access pretty much any position on the disk. But as you can see, this requires some motion, so physical movement, unlike the RAM where any row can be randomly accessed. This okay. So it's not completely the disk is not completely sequential access, but it takes an overhead to access a location. And of course the motherboard also needs to interface with the keyboard. So you recall from the last lecture, the intro lecture, that we used a C in that came from the keyboard and a C out that corresponded to the display. Is this fine? So what we are generally going to bank upon for computation running of our programs is the use of the memory in conjunction with the registers. Program will eventually get saved on the disk, but for most of this class we want to be able to quickly retrieve values in variables, which is possible thanks to the memory. So what are variable names? They are basically sequence of letters, digits and underscore characters. Okay, letters, digits and underscore. Now case matters. So capital ABC, capital A, small bc and small abc are distinct identifiers. So recall that number of sides was a variable. Now tell me, in how many ways can we uniquely write sides? So given that case matters, yes, so you could have a, for this first S, it could be small s or capital S, I could be again small or capital. So how many? 2 into 2 into 2 into 2 into 2 2 raised to 5 is 32. So there are 32 possible unique ways you could name a variable corresponding to sides. You have to choose that which is most intuitive. Obviously, you would choose one of either capital, completely capital, or completely small, or one, the initial one capitalized. Generally, we would advise you to pick the small, lowercase, just for readability purposes. If you have compound, then you could invoke capital. So for example, some capital, for example, you say num capital S ds. So you put a capitalization the moment you have conjoinment of two different words. This is called camel case. There's a hump. Okay. Some words such as small int cannot be used as variable names. They are reserved by C++ for its own use. So exercise for you, tell me which of the following are valid variable names. Small sides, hash sides, third hyphen underscore cousin, third space cousin. Yes? Okay, so this is fine. Hash sides is fine? No, because it should be a sequence of letters, digits and underscore, cannot have a hash. Third underscore cousin, why? Because should not begin with a digit. Third space cousin, space cannot be a part. Tally underscore number, x, third underscore cousin. Okay, so these are all valid. Okay. Also, we would like that our names are very meaningful, so that our program is not a write once, throw away program. We want to be able to build on it. Right? We don't want to be a plastic program. It's already a lot of trash sitting out there. And therefore, we use things like exterior underscore angle in the last intro lecture. And never use single letter variable name unless appropriate in the context. So otherwise, you'll find it unreadable. So what you want to avoid is something like this. U into T, where it's so hard to understand what U was, what T is, plus 1/2 AT square. What do you think U is here? Right? Velocity, right? So this is acceleration, this is velocity, this is time. And what is the expression for computing? So you don't want things to be so cryptic. How does a variable get a value? It is using this very important operator called the assignment operator. Okay, so the equality is not checking for equality, it's actually assigning. Okay, so what's happening is you will have some memory space for exterior angle, and so let's say this was the memory space for exterior angle. What you do is evaluate the right hand side and store the value of the right hand side in the memory location for exterior angle. Okay, so that is an important operation. I'll again illustrate that on the board. Okay, so let's say this was a memory location for exterior angle, EXTE, a long name, exterior angle, and the assignment says that compute the value, compute the following value. Sum underscore exterior divided by num sides. So what you do is compute this value, and after locating where you should be updating in the memory, update. This is how the update happens. So the expression, so let's write down the main part. So you will have a variable name equals expression. So step 1 is to compute the expression. And step 2, assign computed value to the variable. So I have thought of doing the following. Anything that is important that will be used across slides, I'll write it on the board, and anything that's kind of passing, I'll mark it on the slides. Let me know if you want me to follow some other protocol. So we'll need this. Always keep in mind that the step 1 is evaluation of the expression or compute. Instead of computing, let me rename this to evaluate. Right, so the expression itself can be quite complex. So the expression can specify a formula involving constants or variables, right? So I showed you the example of ut into 1/2 at square. That entire thing is an expression. But you have to specifically write down the operator, explicitly write down the operator into. So you can't assume that at is the same as a into t. So the a into t is an expression. At will mean some different variable. So x into in bracket y and z is also an expression. And we'll see lots of expressions in the coming slides. What I want you to do is, for the sequence of steps, capital X equals y, capital Y equals small x plus 2, capital X equals small x plus small y, I would like you to identify what exactly happens with respect to the memory locations. Okay, so assume that we have a table, the memory table. Now we'll associate with each cell or with some of the cells the variables. So let's say this is capital X, this is capital Y, small x, small y, amongst many other variables. What exactly happens when you say capital X equals 5? Yes? Anyone? What gets stored? In the cell for in the row corresponding to x, you will have values 0, 0, whatever, 1, 0, 1. And then, so that's the first step. Capital Y equals small x plus 2. What will happen here? So, small x will have some value. I mean, we don't know what value it has. Some value. What happens when you say capital Y equals small x plus 2? Which location is going to be altered? Yes? The location for y. What is it going to be updated with? You will pick the value from the row for small x. To that you will add, that's going to be binary, so you will do binary addition, and maybe sometime later we will see how to do binary addition, but for the time being, suffice to say that there's some binary addition procedure that you will follow, addition of binary representation of x with that of 2, which is 1, 0, update it in the row for y. What do you do next? You will update the location for x again, right, but this is going to be updated based on the sum of x, small x and small y. Okay, this sum is going to be. So the sequence matters. You can't have capital X equals small x plus small y as a first step and expect the same outcome. So the sequence, as I said, top to bottom and left to right, this entire sequence matters. Any questions on this? We already said that unit of storage is a bit 0, 1. So you may ask why not use a decimal system? Okay, so why not invoke say 10 levels, level 1 to level 10. Now what are we actually dealing with? You already saw the motherboard, the CPU, right? At the lowest level, what are we dealing with? Electrical circuits. We are dealing with voltages. If all storage will be in terms of some voltage. So if I want 0, 1 level, I'll have 2 voltage levels, right? If it's just level, if I restrict myself to level 1 and level 2, then I'll have 2 voltage levels. Otherwise I'll need 10 voltage levels. Now what is the kind of voltage that we are dealing with in our CPU? People who have opened up boxes, the memory, huh? Pardon? No, but what is the voltage level? Are we talking about 230 volts? So 0 to 5, like 2-3 volts, I mean that range. Now if you switch on an AC, you would expect that there's a voltage fluctuation. The supply that is being made to your PC could fluctuate. If you have 10 levels, what do you expect? The chance of 2 levels being mixed up in terms of reading. You ultimately need to read some value. So thresholding becomes a challenge if you have the number of levels. So idea is to keep as few levels as possible for storage so that we don't have loss of information. Is that clear? Okay, so that point is, so the computers are easier to implement by switching the transistors off and on, and it's largely because of this voltage level business. Okay, so that was a side note. Now we said our basic unit will be a byte. Often we'll talk about half of a byte, which is a nibble, right? We take bytes, rats take nibbles. If you've kept food at home and unattended, you will find rat nibbles, which are smaller. So nibble is half of a byte. And we already pointed out that with a byte you can store 256 possible configurations, 256 possible values. And they can all be interpreted as integers from 0 to 255 when you ignore the sign. So that's where we talked of unsigned car, that is what it means. A byte is an unsigned car. Now we'll talk about the sign a little later, signed versus unsigned, but most of the allocation is done in terms of this byte. So a car is the same as an 8-bit byte. More recently people have started looking at multi-byte characters. So if you wanted to only look at, say, the Latin representation, small a to small z, capital A to capital Z, and some special characters, etc., then 8-bit byte is good enough. But suppose we also need you could also have so if you can read Hindi, you could also have Sanyuktakshar, Ja, right? So you might want to give each of these some explicit representation in your byte or your sequence information, in which case people have also started looking at multi-byte characters. But otherwise, we'll assume that we are talking about chars which are 8-bit bytes. So 97 for examples means A, 98 equals B, small b, these are small, 65 is capital A, 66 is capital B, and so on. Okay, so we'll see examples of these. Maybe we can do that right now. So let me just do this. So let me write a char. So 97, and let's try and print out. Let's see what gets printed. Okay, sorry, it's too, the output I can't enlarge it, but it's a small a. The output is a small a. Okay. So 97 corresponds to small a, 98 corresponds to small. You can write simple programs like this to verify whatever we talk about in the class. So you can also compare characters. Why? Because you're dealing with their underlying representation as an integer sequence of bits. So you could, for example, use this property to sort, alphabetical sorting of names in a dictionary. Now you could also have integer types. The previous was char, you could have integer types. For example, you could have short ints, short integers, which are 16 bits wide, and therefore they can store 2 raised to 16 values that corresponds to around 65,500. Those are the number of unique values I could store in a short int. It could be a combination of negative and positive integers, but those are the number of values I can store. It's finite precision. I mean, all of the work is, all of the representations are going to lead to finite precision, because we are ultimately dealing with Boolean, fixed size Boolean representations. You could also have longer 32 bits wide integers, int, and kind of amount to around 4 billion possible values, yeah, which is 2 raised to 32. Okay, this you could write this. So char, int x short y. So short y will take up 2 raised to 16 bits and can take up 2 raised to 16 values. Int x can take up to 2 raised to 32 values. Sometimes you also want very long integers to be accommodated. For example, Aadhaar, right? Aadhaar IDs, plenty in number. Not sure if we can, obviously we can't fit it into just 4 billion given the population of our country. So, so they are called long int, that is 64 bits wide, and that's true. I mean, you have a long in Java as well. Java is another programming language. So long int is 64 bits wide. Now real numbers are represented using float and double, okay, double precision. So we'll see this next. So real representations. Now how do you represent something like 0.314 into 10 raised to 11? Let's say this is what we want to represent. So 0.314 is the mantissa, 11 is the exponent. Okay, so let's try and write this. So short x, and let's say I want to write float z 0.3154 E11. That's how I'd write. Okay, so that will mean 10 raised to 11. So here 0.314 is the mantissa, 11 is the exponent. So mantissa has decimal point at beginning, 0.314. That's what we are referring to here. Decimal point at beginning. So a float has 1 bit preserved for the sign, and again, as I said, we'll talk about sign little later, but 1 bit, some information preserved for the sign, 8 bits preserved for the exponent, right? This is the exponent, 11 as the exponent. So 8 bits for the exponent and 23 mantissa bits. So tell me, what is the size of a float? So this is also 32 bits. I mean, it's the same size as that of an int. See, there's no magic here. You can't expect that the same 32 bits that you use for representing 2 raised to 32 integers will suddenly represent many more number of floats, right? A double, on the other hand, is 64 bits wide, and it has 11 for exponent, 52 for mantissa. Now you might ask, well, why, how do these magic numbers come from, right? So this is all based on experience. This is based on the size of numbers that people need to use for example, high precision mathematics, astronomy, right? So this is coming from experience. Of course, it's not just about large numbers, it's also about very small numbers at the atomic scale. So floats are 32 bit long, double precision 64 bit, and there is an asymmetry in terms of the maximum and minimum value, and we'll talk about it a little later, as I have highlighted there. This is also related to the fact that we are using some information for sign. I'm sorry, I take my word, that has nothing to do with the sign information. It's just related to the fact that we have some restricted space for the mantissa and the exponent. Okay, so but the explanation we'll give later. Now an interesting point here is the finite bits cannot represent all values, all real values. As I said, it's either 2 raised to 32 or 2 raised to 64, and obviously that's not the size of the space of reals. So what's the trade-off? So if I ask you the following, if I say, so let's say I have a float x. Now x is set to 0.314 into 10 raised to 5000 or more, maybe. Just let me put some more zeros, plus 0.314 into 10 raised to minus 50,000, right? Minus 50,000. Do you think the value of x will be any different from the first component? Why? So it is related. I mean, the expected value is supposed to be different, but because of the usage of finite bits, we are going to compromise on very small variations. Okay, hope you got an idea what we are talking about. So the gaps between numbers that cannot be directly represented using reals, using integers that you can represent using reals, but then there are gaps left even by the floating point representation. So you need to exercise some care in writing expressions because you need to avoid errors. So sometimes what you would do is, I mean, of course expressions like this might not be easy to deal with, but sometimes you would try and scale things down, right? You okay. The other thing is if you had multiplications, you could use the log scale and so on. So there are tricks that are employed to get around this value of finite precision. The other point is about initialization of variable. We have been implicitly doing the following. We have been declaring a variable. So we've been doing the following. We said, okay, int I, and then I equals 0. But this I equal to 0 can also be combined into the step that declares, and that is initialization. And you can see the different kinds of initializations that happen here. So Vy is a double 2.0 into 10 raised to 5. I equals 0, that's also initialization. And this value is stored in the variable at the time of creation itself. I already explained to you the character char, so value equals in quote f. Now you can try and figure out in a simple program what the numeric representation of f would be. Okay, so let's stare at this and see whether everything is in order. Your input is here, x equals 2, y equals 3, p equals 4, q equals 5. Are r and s and t initialized? So some of these variables are not initialized, and that can create a problem in the sub steps that follow. So x equals r into s lands into trouble because r and s are undefined. This also highlights that initialization helps. The time you declare, if you could just initialize it. The other steps are all quite intuitive. What we are also trying to communicate to you is the importance of writing these comments. Okay, so try and spend some time on these comments. So what do you expect the variables to behave like is written in these comments. R becomes 2 into 3 plus 4 into 5 equals 26. Okay. Now these may look very silly to you, but as we proceed, you'll realize that absence of comments can make very simple programs look very complex. We'll see more of this. Now a very important point which I mentioned earlier, but I'm going to now we're going to revisit, is that equal to is assignment. Okay, it's not equal, and it's not testing for an equality, but it is a process. It's basically saying that evaluate the right hand side. First evaluate the right hand side, that is step 1, which I mentioned on the board, and then store the result onto the left hand side variable, which is step 2. So if I say d equals ut plus 1/2 at square, obviously d into operations here. Now you could read values of variables from the input. Okay, so we have already seen number of sides as an example in the last class. It's all about reading the value of a variable from the terminal. Let me illustrate with an example. Yeah, so this program accepts as input an integer and checks if it's an even or odd number, right? So I'm going to run it. Unfortunately, when I run it, the size of the output text or the input text is not going to be visible to you, at least people behind, but I'll read out as I type. Everyone can see this program? Yes? Okay, so let me execute it. I'll compile it as well as execute it. So I'm asked to enter an integer, but I'm lazy. I press an enter. what happens? Nothing. I put some spaces, I am spaced out, so I put some spaces, nothing happens. More enters, nothing happens. I put a 6, I enter a 6 and out is a value even. So I asked the program to accept from the cin, the console in, a value of an integer, but it has very nicely conveniently trimmed off, removed all the space and the new line characters that I entered. Okay, so ignores spaces, new lines, etc. This process of taking in the input. I could also take in a char, like I took an int. For example, this could be just f. Okay, so exactly what we observed in the program are written here. User expected to type in values consistent with the type of the variable into which it is read. So, for example, integer for int x, right? If you want to store in x the input value, it better be an integer, but in that process white spaces, space characters, tabs and new lines input by the user are ignored, as I already illustrated, and new line must be pressed after the values are typed. So I had to do that during input. Let's look at the output. So the general idea is x is fed into cout. I could also feed in multiple values to the outputs, x and y both, so x followed by y, or I could also kind of concatenate some strings between x and y. I have done that here, x followed by a comma followed by y, or in the third example position colon followed by x followed by again comma, a string followed and a space followed by y. So I want you to stare at this program, look at the rules. The rules are many values can be printed one after another, need to put a space if you want to have gap between successive values. To print a new line use end L, so we have one end L here, new line. Additional text can be printed by enclosing it in quotes, and then the text position, the position is being typed in here. Right. So now tell me, what do you expect the output to look like? Okay, all of you, open your notes and write down what the output should be. What x is a variable, and cout will be able to access the value of x while printing it. So value of x is going to be printed. So your question, okay, so good question. How do I even proceed without knowing the value of x and y? So let's make some assumption. Let's say that either the user has input or I have set manually int x equals 5, int y equals 6. So this is a semicolon, not j, okay. Get it verified by your, so try and exchange with your friend, see if there are differences, see if you both agree. Yeah, there was a 0, return 0. Oh, that was a complete program. I am only showing part of the program. So the main program has to return something successfully. So return 0 is saying that the program is exiting successfully. So there are some rituals we do. There are reasons for the rituals, but we'll stick to them as rituals in the class. So try and not be decorative and add spaces where there are no requirements. Okay, I mean, I want the output as it is supposed to be. Okay, so there's a 5 followed by this 5 followed by this 6 followed by this 5 followed by a comma followed by a space followed by a 6 followed by position colon followed by 5 followed by comma, followed by space, followed by 6, and then there is a new line, a G on the next line. Okay, everyone got this? Oh, so certainly we have a very messy output and not what we intended to produce. So ideally you should have had an end line in multiple places, an end L maybe here, an end line, end L, and so on. So what are the kind of operations we can perform? Addition, subtraction, multiplication, division, and percentage, which is remainder. So the others are pretty straightforward, but we showed the use of a remainder in our simple code, where we check if an input integer is even or odd. So input integer %2, it does that check, right? Now even characters support plus and minus. So for example, a plus 1 equals b, right? You could do that. Just try this out. Take a, add to that plus 1, and you will find that's the same as b, because the underlying representations are the same. Underlying representations of a plus 1 and of b. You can also try capital Z plus 1. Float and double support plus minus in multiplication and division. Obviously they don't support the percentage operation, remainder, not supported for arbitrary reals. You could also invoke log, x, exponential, sine, etc. from as functions. They are implemented as other functions. And then finally you could compare numbers using operators such as less than equal to, greater than equal to, not equal to, and so on. So it's basically true or false. 0 corresponds to false, 1 corresponds to true. So what will be the value of this? 5 greater than 7? Excuse me, please pay attention. What will be the value of 5 greater than 7? It will be a 0. 4 not equal to 3? 4 is indeed not equal to 3, right? Now some of you asked, what about assigning an integer value to a car? What will really happen? Okay, now we are getting into that field, looking at arithmetic operations between different types, and they are allowed. Arithmetic and assignment operations included. So int x equals 2, y equals 3, z, w are ints, uninitialized. R and S are also double precision values, uninitialized. Now I am going to set R to x. Okay, x is an int, was equal to 2. What will happen is that the representation gets changed, because I am assigning to a double precision number, a variable, an integer value. The integer value will be treated as a double precision value. So it will be treated as 2.0. Z equals q. What would happen? So z is an integer, q is double. So the 3.1 that sits in q, when it gets stored in the value of z through assignment, gets converted into an int, and the value, resultant value is 3. X into q. So now very important, it's important to write down these steps. Okay, so we are going to now map each of these steps. So in the first case, representation was changed, r equals x, and therefore r was assigned the value 2.0. The second example, step 1, store with truncation, that is 3.1 was mapped to 3, and then z was assigned the value 3. What happens in the third case? So first X and Q are converted to the same type. This is an important step. Converted to the same type. Which type? See, X is of type int, Q is of type double. Now, what we will do is see some kind of a hierarchy. When int and double start interacting, both have to talk like doubles, right? So the same type will become double, just because it can exercise more flexibility, more freedom in the range of values it can take. It's very intuitive. So let's write down the translate this into what happens. So this will basically become 2 as a double into 3.1 also as a double. So you can think of it as 2.0 into 3.1. So then you multiply 2.0 into 3.1, and that is 6.2. So you basically now evaluate the expression. It's 6.2. Now it has to be assigned. What is the type of S? Double. So which is fine, there's compatibility. So therefore S is assigned the value 6.2. So the general principle I will write on the board. So when you have an expression right, variable equals expression, you need the elements of the expression to be comparable with each other. So convert elements of expression into the same type. Second step, evaluate. Evaluate the expression. Third, assign to variable the value, right? Evaluate expression to some value, right? You have evaluated the expression to a value. So assign to variable the value as per the type of the variable. We did exactly that in the third case. So variable A and variable B have the same data type, result will be the same data type. So for example, this is about X into Q, right? So if variable A is an int, variable B is an int, then the result will also be an int. If they both are float, then they will be the float. If variable A and variable B have different data types, so for example an int and a float, then the result of multiplication will have the more expressive data type, and I already kind of rationalized that more expressive would be that which gives you kind of more freedom. So in this case we would expect it to be a float, and indeed that's the principle. Int, short, unsigned int are less expressive than float and double. Okay, so when you say into same type, you will upgrade an int to a float if the other one is a float. You will upgrade a float to a double if the other one is a double. Double can accommodate larger values, right? So you will upgrade. So basically it's always upgradation, no downgradation. In general, shorter types, so for example if you have a short, that is less expressive than an int, or a float is less expressive than a double. In this course we largely make use of int and double. So now with this equipment, let's try and decipher what this program will do. Go through these steps. What will this program do? Int x equals 2, y equals 4, p equals 3, double u. What will be your step number 1? So I want everyone to work this out. Step number 1, write down in terms of step number 1. This is my expression. This is my variable. I'll convert elements of my expression into the same type. So what is the expression looking like? X by p is a int by int plus int by int. So what will be the type of each? Since all of them are ints, the type will also remain int. So evaluate the expression as an int. What do you expect the value of u to be then? Now, right, so this is going to be 2 by 3 plus 4 by 3, that is 0 plus 1, that is a 1. So you expect, and now u, it doesn't really matter because right hand side is 1, it will be 1.0 if you want. But when you do a C out on u, it like 0.0 is generally dropped, is my observation. I mean, ideally it should print, but it doesn't print at 0.0. So this will be 1. What will be the value of x plus y divided by p? That is 6 plus 6 divided by 3, which is 2. Okay, see the difference, the same expression but treated very differently. Okay, so you'll have attendance followed by a short quiz.